programs that run on networks to programs that run in networks. And the first talk of that group is Devin, who will tell us about safe modular packet pipeline programming.
Thanks for the introduction. To set the stage, modern computer networks have grown ever larger, ever faster, and ever more programmable. And as a result, network operators and academics like us have sought to run ever more complicated programs inside the network itself. These are called data plane programs, and they run directly on the hardware of the network switches. Modern switches have achieved their great performance by overwhelmingly adopting pipelined architectures, in which incoming packets are processed by a series of stages, each of which does a small amount of computation. Here's an example pipeline with 3 stages, and for our purposes, we can think of each stage as having 2 components. First, it has one or more actions, which are small pieces of computation like a read or a write or an add. And second, it has some amount of persistent mutable memory, which is stored inside the stage itself, and therefore can only be accessed by a packet when it's at that stage. To see how this example pipeline works, imagine we have the following packet coming in from the left. We can think of packets as basically just a struct or a record. In this case, the first stage says we should read the value of G1 and store it in X. Then we'll double that and store it in Y. And finally, we store the result of Y into G2. And now the value of G2 has changed. Any future packet which comes through this pipeline and maybe uses a different action here to read the value of G2 will see the updated value and might do something different later on in the pipeline. Making changes to this stage memory is the primary way in which packets are able to affect the processing of future packets, and so managing this memory is really fundamental to data plane programming. If you want to write a program that compiles down to one of these pipelines, then you're going to need a data plane programming language. The most well-known of these is called P4, and it's a fairly low-level language that more or less directly allows you to manipulate the different parts of the pipeline. In this talk, we're going to be focusing on a more recent higher-level language called Lucid, which is joint work with John Sonczak and Jen Rexford from last year's SIGCOMM. Lucid is built on top of P4, and it provides a high-level abstract view of the network in which packets correspond to events, and when a packet arrives at a switch, the corresponding event's handler is executed. Here we have a simple Lucid program. The instructions in the handler correspond pretty directly to the actions we just saw in the previous stage. And the stage memory in Lucid is represented as a pair of what we call global variables. So each of these will be stored inside a stage during compilation, but notice that the program doesn't specify which stage they should go in. It's part of the Lucid compiler's job to figure that out. However, the program does impose some implicit constraints on this layout because each handler executes in a single pass through the pipeline. This means that since this handler wants to read G1 and then later on write to G2, G1 must be located earlier in the pipeline than G2, just because of this ordering. But you can see how this might lead to problems if we have one handler that wants to use G1 and then G2, and another handler that maybe wants to use G2 before G1. In this case, there would be no way to lay out G1 and G2 such that both handlers are satisfied. This sort of error is called an ordering error, and when we first introduced Lucid, we also introduced a basic type system for detecting ordering errors. We call it pipeline types, and it's a type and effect system where effects correspond to locations in an abstract pipeline. We imagine that we have a pipeline with an infinite number of stages, each storing one global variable in declaration order, and the stages are indexed just by an integer. The type of each global variable is annotated with its location in the abstract pipeline. So G1 here is not just an int, but it's an int at location 0 because it's declared first. Similarly, G2, which is declared second, is an int at location 1. The second part of pipeline types is that During the type checking of each handler, we keep track of our current location in that abstract pipeline. In this example, we'll always start at location 0 because handlers go in a single pass through the pipeline. They always start at the beginning. And on line 5, we try to read G1. We can see from its type that it's stored at location 0. Since we are at location 0, that's great. We'll just do the read, and then we'll move to the next stage in the pipeline. Line 6 doesn't move us forward in the pipeline at all because it's abstract, and it only cares about stages which store global variables. Line 6 doesn't involve any global variables, so it doesn't move us. Finally, on line 7, we try to write to G2. It's at stage 1, we're at stage 1, that's great. We finished type checking this handler at location 2. So this is how the basic system of pipeline types verifies a program. And now let's quickly look at how it rejects a bad program. In this case, we tried to use G2 before G1, even though we declared it after G1. What will happen here is that we'll try to read G2 on line 5. It's at stage 1, we're at stage 0, which is before stage 1, so that's fine. We'll just skip forward in the pipeline, read G2, and then end at the next stage. On line 6, we stay there, and then on line 7, we try to write to G1. It's at location 0, which is before our current location. Since we can't go backwards, the only thing we can do is raise an error. The final piece of basic pipeline types is that Lucid allows users to declare simple non-recursive functions. And as is typical for type and effect systems, the type of these functions include input and output effects. In this case, that means that the type of a function says where you should be in the pipeline when you first call it, and where you will be after it's run. It's also possible to write polymorphic functions. Here we've rewritten the function to take in two arbitrary globals, stored at some polymorphic locations A and B. And the type of this function now says that it goes from polymorphic location A to location B plus 1. There's a little more work we need to do here to make sure that A is actually less than B, and so we're not sneakily moving backwards in the pipeline, but that work is pretty easy to do. At this point, now you have a basic idea of the background and the underlying type system of Lucid. And for the rest of the talk, I'm going to discuss two major extensions to pipeline types that add support for useful modularity features that you probably want to have when you're writing real-world programs. The first of these is abstract data types, and the second one is vectors and bounded loops. To dive right in, let's imagine that you're a Lucid programmer, and being a good practice programmer, you want to wrap up one of your commonly used data types in a module, and you want to put an interface on that module so people can't mess around with the internals and maybe get things wrong. This is the interface for a Bloom filter module. Bloom filters are a super common networking data structure, which are a probabilistic representation of a set. Accordingly, the interface here has three parts. First, it has an abstract type for the filter itself, and it has two operations on the filter, adding an element to the set and checking membership. The filter itself will be stored at some location A, and so the type of these functions says that you start at location A and you end at location A plus 1. They move you forward in the pipeline, consuming the filter when you access it. You could implement a Bloom filter like this. You use a record containing a single array and an integer hash seed. To add an entry to the filter, you hash it using the seed to get an index into the array, and then you set that index to 1. To check membership, you do exactly the same hash and return true if and only if the index is already set to 1. But you can see how this could easily lead to false positives. If two things happen to hash to the same index, you're always going to get the same result for both of them. You could try to improve the precision of your data structure at the cost of using more memory by implementing it with two arrays and two different hash seeds. In this case, to add an entry to the filter, you hash it using each seed individually, which gets you one index into each array, and then you update those indices both to 1. To check membership, you'll return true if and only if both indices are already set to 1. So this is a good way to improve your precision at the cost of more memory, and of course you can do it with 3 or 4, however many arrays and seeds you want. But let's take a second to mentally walk through this function, keeping track of where in the pipeline we are at each line. So the function will start at location A, where the filter is. Then on line 12, we'll access its first component and we'll move to the next stage. On line 13, we'll do it again. And so ultimately, this function's type says that it will move from stage A to stage A plus 2. And that's a problem because the interface said we should be moving from A to A plus 1, moving to the next stage. Really what's going on here is that the function type is leaking information about the implementation of our filter. It's leaking the fact that we have two arrays. So we can think of this as a failure of abstraction. Another way to view the problem is to imagine what the pipeline looks like in each case. Imagine that we declare two filter variables, f1 and f2. If those filters are implemented using a single array, our pipeline will look like this, with one bucket for f1 and one bucket for f2. If they're implemented using two arrays, then each of them will have two buckets. The problem that we're running into is that these two pipelines are noticeably different to the type system. And if we want to facilitate abstraction, we need to find some way to make these two pipelines look the same. The way that we can do this is to draw inspiration from the nested structure of records. In the same way that each of f1 and f2 is a single value which has multiple components, we can imagine grouping these stages together to create single large stages for f1 and f2, which have multiple sub-stages. Now, on the top level, these pipelines do look the same because there's one bucket for f1 and one bucket for f2 in each case. However, this new approach introduces some difficulties. For one thing, it's clearly no longer sufficient to just refer to stages by an integer index, because we need to not just refer to this large stage, but also to its individual substages. There's also the problem that if these subcomponents were themselves compound types, the substage might have its own substages and so on and so forth. In order to address these issues, we actually abandon our linear model of memory as a single pipeline and instead think of our switch's memory as a structured heap. What we've done here is we've created a single virtual root node at the top of the heap, and each global variable is represented as a child of the root going from left to right in declaration order. For each node which is a compound type, it has its own children also going from left to right in label declaration order. And of course, those children could have their own children. Instead of referring to nodes in the heap by an integer index, we'll refer to them by the path to that node from the root. So the new location of f1 is now as the 0th child of r. And the location of f1.r2 is as the first child of the 0th child of r. One really convenient thing about this new sort of list type location is that we can directly compare two of them almost lexicographically to put a total order on the nodes in this heap. And that order turns out to be the pre-order. So we say that children are greater than their parents and right children are greater than left siblings. The fact that we can put this total order on the heap is really the key to why it's safe to take this structured view of memory, even though ultimately we need to lay things out in a linear pipeline. The fact that the nodes are ordered means that whenever we need to, we can just linearize this heap according to that order, so compilation can proceed easily. The final thing I want to bring to your attention about this structure is that f1.r2 here is less than f2 because it is a child of f1, which is itself less than f2. In general, no matter how many children f1 has or how complicatedly nested things get down here, anything below f1 is less than f2. And the reason I stress this is that it's the solution to our abstraction problem. If we go back and look at this add function with our new conception of locations, we'll start at location r.a, where the filter is. Then we'll access f.r1. That's a child of r.a, so we'll access it and move to the next location, ending at r.a.1. On the next line, we'll move forward again to r.a.2. And now, since our current location is a child of r.a, it's sound for us to round up, basically move a little bit forward in our heap to r dot a plus 1. And overall, we can assign the function a type that says it starts at r dot a and ends at r dot a plus 1. This is exactly what we wanted. Now this matches the interface. It says we start at where the filter is and we move to the next thing, consuming the filter. Any information about the internal implementation of the filter type is completely hidden. What we've been able to do now is we've allowed programmers to write any implementation of that Bloom filter module that they want using the same interface. They can make whatever trade-off they want with as many arrays or as few arrays as they want. That's still not quite enough, though, because if you want to make a different trade-off, you need to rewrite the entire module. You got to rewrite the type and the add and any other operations on the type. And that's a big pain, which is made even worse by the fact that in practice, these trade-offs need to be made in a lot of different ways. There isn't one convenient trade-off for Bloom filters, but different applications are going to have different needs. It would be really great if we could provide a way for users to write a single implementation of the Bloom filter type that allows users to choose the trade-off they're making every time they instantiate it. The way that we allow this is to add a concept of vectors to our language. In Lucid, vectors are fixed length lists of values, and we require that the lengths be known at compile time so that we can unroll the vectors and unroll loops during compilation. To see what this looks like in practice, here's a re-implementation of the filter type using vectors. It now takes a size parameter n, which again must be known at compile time, and it has two components. Both of them are n-length vectors, the first one containing the arrays and the second one containing the hash seeds. To operate on vectors, we provide a bounded loop construct for loop variable less than compile time length. Since these loops are bounded, we don't have to worry about termination. And in fact, since we know the lengths at compile time, we don't even have to worry about representing them in the pipeline. We can just unroll them statically. This is what we want our system to look like. The question now is, can we type check it? And it turns out the answer is yes, we can, but there's a tricky part, which is catching errors that occur between iterations of a loop. For example, if you have a loop that always accesses the same global variable, then that might be fine on the first iteration, but once you've accessed it, you move past it in the pipeline. And when you try to read it again on the second iteration, you'll get an error. Another type of error would be accessing two different global variables in a loop. If you try to read R1 and then R2, you'll skip past the entirety of R1 to get to R2. And on the next iteration, when you try to read R1 again, you'll have to go backwards, which is an error. The goal of our type system, therefore, is to ensure that these sorts of cross-iteration errors can't happen. And fortunately, we proved a lemma which says that if they don't happen in the first 3 iterations of the loop, they never will. In other words, it is sound for us to unroll the loops 3 times each and only type check that. For a full proof, I refer you to the appendix of our paper, but as some quick high-level intuition, imagine we have the following loop with the following 3 accesses. Here on the bottom is what our pipeline looks like. We start at some arbitrary stage. Then on iteration 1, we access foo, then bar, then baz. On the next iteration, we'll start on the stage immediately after our previous access. And then once again, we'll move forward a bit and access foo and bar and baz. And notice that the relative position of foo, bar, and baz, or of the 1, 2, 3 arrows, is exactly the same in both iterations, because the type system ensures that their relative position in memory will always be the same. On iteration 3, we get something stronger where all of the arrows, including the start arrow, are in exactly the same relative position as in 4. So hopefully it's not too hard to believe that if we were to keep going past this point, every new iteration would just have exactly the same pattern of arrows. There's no room for variation or divergence, which means there's no room for errors. If something was going to go wrong, it would have had to happen before this. Okay. think we're running a little short on time, so here I just want to mention that Lucid is not the only high-level data plane language, but it is the only one that has this concept of an ordering error. So if you try to write a program in one of these other languages that includes an ordering error, then the compiler will usually just fail with an unhelpful error message. To sum up, last year in SIGCOMM, we introduced the Lucid language and showed that it's actually useful in a networking context. And now we've shown that its type system can be expanded to handle modularity features that you probably want to have when you're writing real-world programs, such as abstract data types and parametric vectors. So we hope that the ideas of pipeline types can find traction in other languages besides Lucid, and maybe even in other settings outside of networking that use pipelines, such as signal processing. Thank you for listening. I think we have time for some questions.
All right, we'll start with an online question. Your running example seems to miss the opportunity to parallelize operations across hash tables. Is that an inherent limitation of the hardware? And have you thought about targeting more flexible hardware like FPGAs?
So there is some parallelization that will happen automatically in the compiler that we don't show here. So each stage of the pipeline has the ability to do a bunch of different operations, and frequently our compiler will be able to do things like, in fact, it can store multiple globals in the same stage as long as they don't have a data dependency on each other. So it might be able to, for example, do this entire add function in a single stage if the rest of the program, if things work out, basically. We have thought about targeting other backends like FPGAs with Lucid. We haven't really moved forward on it yet, but one of the goals of the language's development in the future is to have a retargetable backend for other switches, or, as you say, things like FPGAs.
All right, we have a local question.
Hi, thanks for the very interesting talk. So it seems like a lot of the problems that you run into are due to the insistence on kind of a concrete integer pipeline with like a totally ordered, discrete time steps. Why could you provide some motivation for why you don't think of it more abstractly? For example, pipelines are just, each stage of a pipeline is just an abstract element of a set, and maybe you have a directed acyclic graph of dependencies between them. Like why, and even in your heap generalization, it's very concrete, right? So what's the motivation for it being, concrete integers assigned to each stage of the pipeline?
So correct me if I'm wrong. It sounds like you might be wondering why we're sort of fixing things in advance instead of trying to infer a possible order. Is that accurate?
Sure, yeah, right.
Yeah, so the answer is we can do that, and in fact, it's not even too difficult to do it as a tweak of the existing thing. Basically, you do exactly what you said. You assign abstract locations to global variables instead of concrete things. The downside, and the reason we chose not to do that, is that in the event of an ordering failure, it's much harder to give useful information back to the programmer. In Lucid's conception, ordering errors are always a conflict between the program as written and the declaration order of the globals. So we can always point to line 7 right here as, here's where you did something wrong, fix it. If you try to infer an order, then you might have a whole bunch of different parts of your program which are involved in making no order exist. And it's just much harder to explain what went wrong to a user in that setting.
Thank you.
All right, one more local question.
I think this is a really cool system that exposes good error messages in a difficult domain. But I had a question, and maybe this is inherent to the domain too, but there are no branching constructs here. And the one big difficulty, it seems, with introducing branching constructs is that it seems
Sorry,
like...
You're very quiet. I didn't hear anything after.
So there are no branching constructs in your language, which might be a limitation of the domain. But it seems like one of the biggest difficulties with introducing branching constructs would be that it would immediately invalidate your triple unrolling lemma for the loop. So, do you imagine a possible generalization of that lemma that could work even in the context of branching?
Yeah, so in fact, branching is allowed in the language and is handled by the type system. I just didn't bring it up in this talk. The way we handle branching is sort of standard for type systems. We just unify the branches on each side. And so if one branch ends at location 3 and the other ends at location 4, then after the two branches, we'll end at location 4, the greater of the two. And it turns out that basically, since we can then view branches as sort of abstractly as just one thing that takes you to location 4, we don't have to worry about, we can just treat it like a single access for the purposes of the enrolling lemma. So it doesn't actually cause any problems.
All right, we'll have one more remote question. For abstract data types, my first intuition was to allow multiple variables at the same stage. Is the issue with this that we'd be forcing potentially too much code or data at one stage on the switch?
The issue is, well, so yes, that's one problem. But we can also think of we could also imagine an abstract pipeline with sort of arbitrary width stages. I think I would say the goal of this type system is to ensure that some order exists. And certainly if an order exists, the compiler is allowed to make optimizations and put multiple things in the same stage if they don't depend on each other. And if we had a bunch of things in a single stage and it turned out we couldn't fit that many things into an actual stage of the pipeline, then I would start to worry that maybe it's not actually compilable, or maybe no order exists, even if we had an infinite number of stages. Another another concern is that we want to even if we have things in multiple stages, they're not allowed to interact with each other. So putting things in multiple stages isn't a problem or isn't a solution to something like this. Even if we could do all three of these in one stage, we wouldn't be able, it would still be an ordering error because G1 needs to come strictly later than G2.
All right.
Great, thank you.